Hello, my name is Gonzalo Abad, and in this presentation I'm going to do a short introduction to electric drives for traction applications. The content of this presentation is a summary of Chapter 1 of this book, Power Electronics and Electric Drives for Traction Applications, edited by Wiley in 2016. So let's have a look at the content of this presentation. First, we will describe some few traction applications. Then we will describe the electric drives, and after that we will see different types of electric drives. And finally, a brief classification of the parts that compose an electric drive will be seen. Okay, so let's move. So let's have a short look of how works an elevator, which is the first traction application that we are going to describe. First of all, we have the shaft and the ropes. Mechanically coupled to the shaft, we have an electric motor. The rotational movement created by the motor makes rotate also the shaft, what means that the ropes are also moved. Connected to the ropes, we normally have the car where the passengers move up and down. And then also we have the counterweight, basically to make the energy consumption of the motor more efficient. Therefore, we can see how controlling the rotation of the motor, we are able to control the car of the elevator, which means that we are able to control the elevator itself. Here in this figure, we have an example of a simplified picture of an elevator from company Aurora. Okay, let's have a look to another application, which is in this case the electric vehicle. In an electric vehicle connected to the wheels by means of a special mechanical transmission, we have an electric motor. In an equivalent manner to the elevator, the rotation of the wheels is generated by the rotation of the electric motor. And therefore, as it is well known, the linear movement of the car itself is a shift. There are different configurations of the electric vehicles, but we can say that nowadays this is the most commonly employed ones. Finally, now we can see here an example of a smart electric vehicle. Another similar traction application is regarded to the Revel Traction. There we can find locomotives, trains, trams, and so on. In all these cases, the traction force is created in a very similar way as in an electric vehicle. Normally, at least, there is a traction bogie as simplifiedly shown in this figure. And the wheels of this traction bogie are moved by one or more electric motors. Therefore, again, the rotational movement of the motors produces the movement of the wheels and consequently the movement of the train itself. Once again, we have here an example of a real tram from the company CAF. Finally, one similar application to the ones mentioned before could be the ship propulsion. Modern ships nowadays are electrically propelled. As can be seen in this figure, at the ship there can exist one or more thrusters or propellers, which rotation is controlled again by an electrical motor. As in previously seen devices or applications, by moving faster or slower the motor, we can make the ship, in this case, move also quicker or not. Once again, here in the picture, we can see a real example of a modern vessel based on electric propulsion from company Ulstein in this case. Moreover, Up to now, we have seen 4 typical applications which operates thanks to an appropriate movement of an electric motor. But here in this table, we can see an enumeration of different equivalent applications based on the same movement principles. Hence, in most of the traction applications, it is possible to distinguish some certain repetitive patterns or loads. In other words, the motor that is in charge of the movement, depending on the nature of the application, can find a load in opposition, such as, for instance, in conveyors, constant torque load at different speeds, or in elevators, constant speed at different torque loads. Another very common load torque profile is parabolic function of the speed, as seen in this picture. For instance, pumps, fans, ships, and so on. There we can also find hyperbolic profiles like in windows on ladders, or finally also some more non-symmetric profiles like in crushers or mills. Okay, so let's describe now the electric drive. Hence, as it is known, the motor by itself is not able to control the movement. It is necessary further elements based on power electronics, enabling to perform an appropriate control of the motor. In general, this element is commonly called electric drive. Depending on the application itself and their needs, it must be specially designed, but normally it presents a fixed or well-established structure. Therefore, typically we have a load that we are required to move, for instance, the shape of an elevator or the propeller of a ship. Then, as we have described before, we mechanically couple to the load the electric motor that produces the rotational movement. Thanks to the motor or machine, we are able to produce adjustable and controlled speed here. In order to create this movement, we often need energy. This energy is taken from an energy source, which typically is an electric energy source. Therefore, we need also a power electronic converter which takes appropriately the energy from the energy source and delivers it to the electric machine or motor. This power converter provides instantaneously the appropriate amount of energy to the motor by applying the appropriate adjustable voltage at the motor terminals. In general, the energy source works at fixed voltage while the motor works at variable voltage. Finally, but no less important, it is necessary a control algorithm which is in charge of controlling the whole system according to the specific needs of the application. It can be communicated with all the elements of the system, but it basically sends order to the power electronic converters. It can be also interfaced with the user, as for instance in a train when the driver demands a certain traveling speed. Therefore, the group of electric machine, power converter, and control algorithm is called electric drive. Note that depending on the application needs, the flow of the energy can go in both directions or only one. However, in general, at each application, there is only one dominant direction for power flow. Therefore, going into more details, we know that the electric machine moves the mechanical load, what means that the control of the rotation of the mechanical shaft at certain speed. Depending on the application and the momentaneous operation conditions, the load will produce a certain load torque at that rotational speed. And therefore, in order to create an equilibrium at the speed, the machine will be in charge of creating the required load torque. And as commented before, in general, the specific operation condition of the movement might require the capacity to obtain adjustable speed and torque. For instance, in an electric vehicle, from journey to journey, it needs to move different number of passengers and therefore different weights. Hence, in order to obtain this adjustable torque and speed, we need to supply the electric machine at voltages of adjustable amplitude and frequency. These voltages are typically AC, and in most of the cases, high amplitude and frequency is associated to high rotational speeds, while low amplitudes and frequencies are associated to low speeds. Often also the amount of current consumption of the machine is associated to the load torque. On the other hand, these voltages of different frequency and amplitude needed by the machine are created by the power electronic converter. This element enables the energy flow from the energy source to machine with the appropriate characteristics. Note that in general, depending on the nature of the energy source, it is on itself or of fixed voltage in DC or AC. Finally, it has to be mentioned that at least nowadays the power converters are still not able to produce pure sinusoidal voltages. In contrast, depending on the nature or topology of the converter itself, it creates waveforms of different voltage levels with more or less similitude to the ideal sinusoidal shape. Okay, so let's continue with the contents. So now we are going to present the most typical electric drive configurations used nowadays, according to the conversion system used. The first one is the electric drive with DC-AC power converter. As usual, we have a general load that must be moved. And then we have the electric motor that is supplied with the DC-AC power converter, taking the energy directly from a DC voltage source. In this case, in principle, the power flow can go in both directions, whenever the DC supply source is prepared for that. Finally, here we can see an example of this electric drive configuration with a two-level power electronic converter. Hence, the next electric drive configuration is similar to the previous one, but it incorporates a DC-DC converter at the input. This configuration in general requires two separated control algorithms, one for each conversion stage, as represented at the picture. In principle, it can be said that the necessity of the DC-DC conversion stage arises when the DC source experiences a quite significant voltage variation because of its nature, as for instance a battery pack. In this way, the input converter enables the DC-AC converter to operate with constant input DC voltage. In this case again, the power flow can be in both directions. And here we can observe a simple example of this electric drive type. Okay, so let's have a look now of the electric drives with unidirectional AC, DC, AC converters. This conversion system is required when the source that we face is AC. As usual, we are required to move the load. Then we have the electric motor and the DC-AC power converter with its corresponding control. And at the input we put an AC-DC converter based on diodes, for instance. In other words, a passive front end. Obviously, in this case, the power flow can only go in one direction, which is from the AC source to the load. Here in the figure below we have an example of this electric drive with a 6-pulse rectifier as input converter. If the application punctually requires to absorb energy from the load, it is possible to incorporate a DC chopper for regenerative braking. Following at the same scenario with an AC source, it is also possible to find an electric drive with an AC-DC-AC conversion system. In this case again, we have the typical DC-AC converter supplying the machine and load. While in this case, at the input we include a controlled AC-DC rectifier based on control switches. As can be noticed, both converters need their own control algorithm for proper operation. Thus, thanks to the conversion philosophy, it is possible to guarantee a power flow in both directions, whenever the AC source is prepared for that. Hence, in this picture below we can see an example of the bidirectional conversion system, often also called the back-to-back conversion system. In this case, both converters, the AC-DC and the DC-AC converters, are chosen as two-level converters. However, any other topology could be also used. If the grid, instead of being three-phase, is single-phase, we could also use a single-phase conversion system at the input stage as represented in this new figure. Finally, it has to be mentioned that many other electric drive configurations can be found attending to the conversion stage used. However, for simplicity, only the most relevant ones have been presented up to now. Okay, so let's move. So now, briefly, we are going to enumerate the most commonly used parts in an electric drive. We will have a quick look at the power converter, the machine, the control, and the external energy source. First of all, we will start with the power converters. But before we do that, let's briefly speak about the semiconductors that typically form the power converters. Thus, this table shows the most commonly used controlled and non-controlled semiconductors, together with their typical symbol. We see here the diode, the thyristor, MOSFETs, and so on. As an example, here we can see some power modules of IGBTs from the company Infineon. Okay, let's have a short look now of the most typical power converter topologies used. First, in this table, we have the diode rectifiers that can be of 6, 12, 18 or 24 pulses and even more configurations. From the point of view of the controlled voltage sources, the two-level converter probably is the most established one. However, especially at higher power applications, multi-level conversion structures are being more and more used. In this way, the three-level MPC converter probably is the most popular one. We can also find the four-level flying capacitor conversion structure. When 5 levels are required, the 5 levels active MPC is a very optimized conversion structure. Well, there are many other converters topologies that, however, they are out of the scope of this enumeration. With regards to the DC-DC conversion systems, here there are some few examples. For instance, the flyback is a very popular conversion structure. Or for instance, the dual active bridge is an example of a more sophisticated DC-DC converter. Finally, in these two pictures, we can see two examples of real high-power converters from company Ingeteam and CAF. The first one is used at industry applications, while the other is used in Revel Traction. Let's move now to have a quick look of the typical electrical machines that we can find nowadays. Here again, there exists a huge amount of machine philosophies, but only the most significant ones are shown in this table. Probably we can say that the squirrel case induction motor is one of the most extended machine designs. Then, within the family of synchronous motors, we have the Bloomfield synchronous motor that in general need an external converter to supply the rotor field. Then we also have the synchronous reluctant machine, as shown in this figure. And also we can find permanent magnet synchronous machines with magnets located at the rotor superficially or inwardly. Then also we have the brushless DC motor, or even the variable reluctance motor or stepper motors. Finally, we can see here two examples of real machine designs. The first one is a permanent magnet synchronous motor from an elevator of the company Orona. The second one is a submergible induction motor from company Ingeteam, typically used in dredges. Now let's go to the control algorithms that mostly are used. In this case again, we can find a huge amount of different control philosophies employed. However, probably the most extended ones at real products are some few. Scalar-based control provides limited performances, and therefore they are used in not many applications nowadays. Then probably the most used one is the vector control strategy, because it provides very good and adaptable performances. Then we can also find direct torque or power control strategies, and also predictive control nowadays is taking a significant place. Finally, we can see here one example of DS-Space, which is an example of the control hardware where these controls can be implemented. To conclude, let's also enumerate the most typical energy sources that we can find among different applications. The most typical one probably is the electrical grid that is available in many houses and companies all around the world. Then we have AC catenaries for Revel Traction. We have also AC generators moved by a prime mover and used, for instance, in hybrid vehicles and ships. As DC sources, batteries are very much used in many applications. And supercapacitors, often supporting another primary source, are typically used as well. Then we have also DC catenaries for Revel Traction, and maybe more elements not enumerated here. Connected to this, let's have a look of the materials needed for constructing these elements present in an electric drive. Thus, for doing semiconductor and microprocessors, we basically need silicon. However, we also need copper, silver, and some other elements for doing base plates, unit between chips, etc. Then, for doing electric drive machines and inductive elements such as filters or transformers, we need copper, steel, magnets, materials for insulation, etc. And finally, for batteries and supercapacitors, for instance, we need different chemistries and materials. So, from an electronic point of view, for applications or devices of our daily life, we need electric motors, power converters, energy sources, and control hardware such as microprocessors. And these elements are made of some other basic materials such as silicon, copper, magnets, and so on, which are at the same time taken from mines, solar, sand, etc. And this is what we have. Hence, this gives us a short look of the materials needed for electric drive technology. To conclude, I can only say that much more information related to this technology can be found at this book. Thank you very much for your attention.